When I was young, I had a dream of being a striker of the Borussia Dortmund, working with many world-class football stars. One of the fundamental skills of the football striker is the movement. The base striker like Erling Haaland, Robert Lewandowski often hide themselves behind the opposition defenders. They need to reposition themselves time by time to look for the scoring opportunity. Finally, they will enter the game. Hello everyone, so my name is Yue Yang. I'm a second year PhD student of the University of Sydney. This video I will talk about the repositioning problem, but not in the football, it's in the red heading system. This is a joint work with my supervisor, Ramezani, and this paper has been published on the IEEE Transactions on Intelligent Transportation Systems. From perspective of vehicles, the hailing service can be divided into three stages. The first stage is searching. The vacant vehicles cruise or park on the street until they have been assigned to a passenger request. The position receives the dispatching order is called the dispatching point. The second stage is picking up. Assigned vehicles from their current dispatching point head for the origin of the order to pick up the passenger. The final stage is serving. Occupied vehicles take the passenger to the destination, and they will start searching again. So the repositioning problem is that to answer the question, where is the best location for the vacant vehicles to find the passenger at the searching stage? To tackle this problem, the integrated repositioning approach is developed to consider both the long-term efficiency and real-time information in a centralized and coordinated way. By modeling the repositioning and the sequential decision-making problem, the single-agent MDP model is used here to generate the optimal policies and evaluate the long-term influence of the repositioning on the system efficiency. By accounting for the passenger's waiting time in real time, the real-time matching between the multiple drivers and repositioning destination is formulated as the optimization problem and served using the binary linear programming. We use the BOP and the short of this method. In the final stage of the integrated repositioning, the priority is set to the real-time optimization. The vacant vehicles with the no-zero BOP solution are firstly repositioned to the destination with the higher service priorities. And after that, the idle drivers with the all-zero BOP solution will follow the MDP solution to optimize the long-term efficiency. In this video, we use offline learning to represent the MDP model, and we use the hexagonal grid to represent the mapping in the e-hailing system. And next, we will introduce the state, action, and reward for the MDP formulations. The state of the vehicle, which consists of the three elements. The first two are current hexagon and the time state of the vehicle, and the last one is the operation status of the vehicle, which might be the searching or picking up and serving. The repositioning problem is just for the searching vehicle. And the action, which consists of the two subsets. The first one is the neighbor action space, which consists of the neighbor hexagon of the current hexagon. And the second one is the global action space, which are a global hotspot in the system. And once the vehicle arrive at the represented destination, and if they receive dispatch orders, we set the reward function, and the one divides the repositioning distance. And finally, we serve the MDP model by the dynamic programming algorithm. For the online optimization, we use a binary linear programming to serve this problem, and we introduce the XHK and the minor decision variables between the hexagon H and the driver K. And the object function is also the weight function on each driver hexagon pairs. It's the total waiting time of the orders in the hexagon H divides the travel time from the driver location to this hexagon. And we also introduce two constraints for this model. The first constraint is guaranteeing the vehicle will be assigned to at most one hexagon. The second constraint ensures the number of the repositioning vehicles to this hexagon is less than or equal to the maximum capacity of the hexagon. This aims to avoid representing too many vehicles to the same hexagon. For the numeric results, we use a Manhattan neural network to test our method. For the demand, we use open source trip data from New York, and we generate the drivers by a time varying and stochastic distribution in the 3 regions of the Manhattan. And we introduced a 5 benchmark method and named our proposed method the real-time multi-driver. And based on the result, we found that the proposed method outperforms other 5 repositioning benchmarks with regard to the platform efficiency. We can found the proposed method can reduce the cancellations and achieve the higher response rate. And we can also found the proposed method could enhance the passengers' experience by reducing their waiting time, and it can also bring substantial benefits for the drivers to increase their occupied rate. Thanks for your attention. If you're interested in this work, you can find the 4 papers in the below link. Goodbye.